Okay, so I want to start today with a little thought experiment.
Uh-huh.
If I were to, slide a document across the desk to you right now, a PDF titled FAA Airworthiness Directive 2025-2604, what is your honest gut reaction? Be real with me.
Oh, honestly, my eyes just glaze over.
Right.
It sounds like a cure for insomnia. I mean, that is bureaucracy in its purest, driest form.
It does, doesn't it? It sounds like paperwork. Just a string of numbers and dates, but, and this is why I absolutely love digging into these things, hidden inside that incredibly dry title is actually a high-stakes thriller.
I believe it.
We are talking about massive kinetic energy, structural failure, and, well, fire. And it is all happening inside one of the most common engines flying in the sky today.
And that's the deceptive thing about aviation safety, isn't it? The most terrifying stories are usually hidden behind the most boring acronyms.
Yeah.
And today, we are focusing on a very specific piece of heavy metal, the Pratt & Whitney PW1100G-JM.
Which the industry knows as the Geared Turbofan, or GTF.
That's the one.
It's the massive engine powering the Airbus A320neo family. I mean, you see these things at every major airport in the world. If you look out the window, it's that giant nacelle staring back at you.
You do. It's a workhorse. It's a revolutionary engine, really, because of that gear system. It allows the fan to spin at a different speed than the turbine, which makes it incredibly efficient. But like any complex machine pushing the boundaries of physics, it has its vulnerabilities. Now, if you've been following the industry chatter lately, you might think the biggest problem with the A320neo is software.
Right. I've seen the bulletins about the ELAC solar radiation patch and all the digital updates. It feels like we're constantly talking about glitches, turn it off and on again.
Exactly. We fix planes with laptops these days.
Yeah.
But this deep dive is different.
Okay.
We aren't talking about code today. We are talking about hardware, physics. This is a physical, mechanical threat that the FAA and operators are, well, scrambling to fix as we speak.
And the mission for this deep dive is to unpack exactly what that threat is. The sources describe a failure chain that is fascinating and, frankly, a little terrifying.
It is.
It's like a Rube Goldberg machine, but instead of cracking an egg at the end, it starts an engine fire.
It is a classic domino effect.
Yeah.
One component fails, and it triggers a sequence that ends in a very dangerous place.
Right.
And what's interesting here is that the component that starts the fire isn't even the one that failed first. It's a victim of circumstance.
So let's play detective. Let's walk through this chain reaction step by step. Where does the first domino fall? Because the source material points to a very specific, very violent trigger event.
It starts with an FBO event.
FBO.
That stands for fan blade out.
Which is pretty much exactly what it sounds like.
It is. You have these massive titanium or composite blades at the front of the engine. An FBO means one of them fractures and separates. Now, usually this is a bird strike.
Nature versus machine.
Yeah, you hit a goose at 150 knots.
Yeah.
But it can also be material fatigue over time.
Just so we can visualize the scale here, we aren't talking about a plastic fan blade snapping off a desk fan.
No. Think about the energy involved. These engines produce tens of thousands of pounds of thrust. The fan is spinning at thousands of RPM.
Okay.
If you lose a blade, you are suddenly losing a significant chunk of mass in a finely balanced system. The result isn't just a noise, it's an explosion of kinetic energy.
The balance is gone.
Instantly. You get what we call massive imbalance loads. The engine starts vibrating violently.
Yeah.
And I don't mean a little shudder like driving over a rough road.
Right.
I mean the kind of vibration that blurs your vision and makes it hard to read the instruments in the cockpit.
Oh, okay, so here's the physics question. You have this massive vibration at the front of the engine where the fan is. Does that energy just stay there?
No. And that is the crux of the problem. Energy has to go somewhere. It travels. It transmits backwards through the engine case. It's essentially a shock wave looking for a place to dissipate. It ribbles through the structure like a ringing bell.
And it finds a weak link.
It does. The sources identify the specific component that takes the hit. It's called the TMS clevis mount.
TMS, that usually stands for thermal management system, right?
Correct. So deep inside the engine cowling, there are these brackets clevis mounts that are designed to hold components of the thermal management system in place.
Okay, so they're anchors.
They are structural anchors. But in this specific scenario, under those massive violent imbalance loads from the broken fan blade, the TMS clevis mounts fail. They simply aren't designed to handle that specific frequency and intensity of vibration. They snap.
Okay, so now we are 2 steps into the chain. We have a broken fan blade at the front, and because of the shaking, we have a broken bracket deeper inside.
Right?
But why does a broken bracket lead to a fire? That's the leap I was struggling to make when I first read the AD.
And this is the critical domino you have to ask. What were those mounts holding?
Okay.
They were supporting the CP09 tube assembly.
The CP09 tube, that sounds innocent enough. What is flowing through that tube?
High-pressure fuel. Specifically, it's the hydraulic fuel pressure fuel oil cooler tube.
Oh.
So picture this. The mount snaps. The tube suddenly loses its support. But remember, the engine is still vibrating violently because the fan is still spinning down.
So the tube is essentially flailing around in the dark.
It's unsupported and being shaken to its core. It's whipping back and forth. The result is that the CP09 tube fractures. It cracks open.
And now you have high-pressure fuel spraying out inside the engine cowling.
Exactly. And it's spraying directly onto hot engine components. The engine case is hot, the compressed air is hot.
Which gives you ignition.
You get an under-cowl fire or a pool fire. The fuel pools at the bottom of the casing and ignites.
Wow.
And the FAA has confirmed 3 specific instances where the exact sequence occurred. Fan blade out, mount breaks, tube cracks, fire.
That is wildly unsettling. It really highlights how interconnected these systems are. You can design a fan case to contain a loose blade, which they do. That's a certification requirement. But you also have to consider what the shockwave of that failure does to a tiny bracket 5 feet away.
That's the challenge of aerospace engineering. You weren't just designing for normal operations. You were designing for the worst day of that engine's life.
Yeah.
And in this case, the design of that bracket didn't account for the worst day's scenario well enough.
So we have a clear failure chain. Now let's talk about the solution, because the FAA isn't just pointing this out for fun. They've issued Airworthiness Directive 2025-2604, and the timeline here seems incredibly aggressive.
It is very tight. The effective date is February 17, 2026.
That is right around the corner.
It is. Airlines don't have months to sit on this. They have to act.
Okay.
And the fix is fascinating to me because it is split into 2 phases. And phase 1, the immediate fix, is completely counterintuitive. I actually had to reread the engineering bulletin to make sure I understood it.
I felt the same way. Phase 1 is called the interim action, and to make the engine safer, they're asking maintenance crews to remove a part.
Correct. They have to remove a specific loop cushion clamp from that CP09 tube assembly, part number ST1-54006, for those keeping score at home.
Let's unpack this logic. Usually, if something is breaking because of vibration, your instinct is to clamp it down tighter.
Right.
You want to secure it. Hold on for dear life, right? But the FAA is saying, take the clamp off. Why?
It's a paradox, isn't it?
Yeah.
But here is the engineering reality. The analysis showed that the original clamp was creating what we call a stress concentration point.
Stress concentration. Break that down for us.
So imagine you are holding a thin stick or a ruler. If you hold it loosely at the very ends and someone shakes it, it bends, it flexes, it absorbs the energy.
Okay.
But if you clamp your hand tight in the dead center and someone tries to bend it, where does it snap?
Right, my hand.
Exactly. Because you've created a hard point. You've prevented the material from distributing the stress. By having that clamp there, they were inadvertently forcing the tube to absorb all the vibration energy at one specific spot.
I see.
And that's where it was cracking.
That makes perfect sense when you visualize it. The clamp was making the tube too rigid.
Rigidity is often the enemy in dynamic environments. So by removing the clamp, they're actually increasing the flexibility of the fuel tube.
Ah.
If the TMS mount breaks during a bird strike, the tube can now flex and wobble with the vibration rather than snapping. It keeps the fuel inside the line.
So the goal is to let it dance so it doesn't break.
Precisely. Flexibility leads to survival.
And this has to happen fast.
Within 30 days, the effective date. So maintenance hangars are going to be very busy pulling these clamps off. You're going to see a lot of overtime in the MRO, the maintenance, repair, and overhaul shops this month.
But that's just phase 1. That's the flex fix. There is a phase 2, which the source calls the terminating action. And this seems like the more permanent solution because presumably you don't want a fuel tube hanging loose forever.
Right. You can't leave the tube unclamped for the next 20 years. You ideally want it supported to prevent other types of fatigue, but you can't support it with the weak mounts.
Right.
So phase 2 happens at the next engine shop visit.
Now, shop visit sounds casual, like taking my sedan in for an oil change. But in aviation, that term has a very specific, very expensive definition, doesn't it?
It does. The FAA defines it strictly. It includes any induction involving the separation of major mating engine flanges.
Separating flanges, that means cracking the engine open.
Essentially, yes. Even a quick turn visit counts.
Yeah.
If you are opening up the core to get to the guts of the machine, you have to do the phase 2 fix.
Right.
This isn't something you do at the gate while passengers are boarding. This is heavy maintenance.
And what is the hardware change in phase 2?
They are replacing the TMS clevis mounts, the weak link we talked about at the beginning, with a redesigned, stronger version. These new mounts are beefy enough to withstand the loads from a fan blade-out event.
So, stronger anchors.
Stronger anchors. And here is the twist. Once those stronger mounts are installed, they reinstall the loop cushion clamp.
Ah, okay. So we do want the clamp back eventually.
We do. We want the stability that the clamp provides, but we can only afford to have that stability once the foundation, the mount, is strong enough to ensure it won't snap and transfer all that stress to the tube.
That is a really elegant bit of engineering problem solving. It's like saying, we can't hold it tight yet because the foundation is weak, so let it be loose for now, fix the foundation, then hold it tight.
It's a great example of managing risk in real time. You mitigate the immediate fire risk with flexibility, that's phase 1. Then you solve the structural issue with reinforcement, which is phase 2.
So that's the view from the hangar floor. Mechanics are removing clamps and swapping mounts. But I want to shift perspective now. I want to go upstairs to the flight deck. Because if this failure chain kicks off, if a bird hits the fan at V1, the mechanics aren't there. The pilots are.
The view from the sharp end. This is where the engineering reality meets the human reality.
Right, because the pilots are the ones who have to manage the chaos. The source material outlines some very specific scenarios that pilots need to be aware of now that we know about this failure mode. Let's look at scenario 1, the vibration event.
Okay, you are taking off. You're at high power. Suddenly, bang, a bird strikes. You feel a massive shudder through the airframe.
What is going through the pilot's mind at that exact second?
Well, traditionally, your training kicks in for severe damage or engine failure. You are looking at the N1 gauges.
Yeah.
But with this AD in mind, your mental model has to shift slightly.
How so?
You have to anticipate that the damage isn't limited to the fan. You have to anticipate that the vibration is breaking that fuel tube right now.
So the golden rule here is expect fire.
Yes. Do not be surprised if you get a fire ENG 1 or 2 warning shortly after the vibration starts. And this changes the urgency of the procedure.
The source mentions a specific procedure to stop the leak.
Right. If that CP09 tube fractures, you have high-pressure fuel pumping out. It's feeding the fire. The fire extinguishers won't put out a fire that is being actively fed by a fuel pump.
That makes sense.
It's like trying to blow out a candle while someone is spraying gasoline on it. The only way to stop it is to close the low-pressure, the LP fuel valve.
And how do they do that?
By hitting the master switch to OF.
So speed is key. You can't hesitate.
You don't want to rush the memory items and make a mistake. We always say slow is smooth, smooth is fast. But you must execute them decisively. Every second that valve is open, fuel is spraying.
Now this brings us to scenario 2, which honestly gave me a bit of anxiety reading it.
Huh?
The button problem. This feels like a cruel joke.
This is where things get complicated. The source connects this issue to another directive, EASA AD 2025-0274.
We're layering ADs now. It's an alphabet soup of problems.
Unfortunately, yes. There have been reports of fire panel push buttons being faulty.
What do you mean faulty?
Specifically, they were self-releasing or failing to latch when you press them.
Imagine that. You have a fire warning screaming at you. The plane is shaking. You reach up to push the fire button to arm the extinguisher squibs, and the button won't stay in.
It is a nightmare scenario.
Yep.
The button pops back out. If it pops out, the extinguisher isn't armed, and the hydraulic and fuel valves might not close fully.
Oh, wow.
The advice from the technical briefing is very explicit. Pilots must firmly press the fire button until they see the verification that the squibs are armed. You can't just tap it. You have to make sure it latches.
That is such a critical detail. If you're dealing with the vibration, the adrenaline, and the alarms, you might not notice the button popped back out if you just gave it a quick press.
Exactly. It adds a layer of physical confirmation to the procedure. You have to fight the machine a little bit.
And if that wasn't enough, we have scenario 3, the smoke.
Right.
Because it's not just fire you might be dealing with.
No. This involves a system called the load reduction device, or LRD.
What is the LRD supposed to do?
It's actually a safety feature. When the fan gets wildly unbalanced, the LRD allows the shaft to pivot or decouple slightly to prevent the whole engine from tearing itself apart.
So it saves the structure.
It saves the structure.
That's always a but.
But when the LRD activates, it compromises the oil seals in the bearing compartment. It allows oil to leak into the airstream.
And that airstream is the bleed air that pressurizes the cabin and the cockpit?
Correct. So if oil gets in there, it vaporizes instantly on the hot components. You get heavy, acrid smoke pumping directly into the flight deck.
So let's paint the full picture for the pilot here. You have a bird strike, the plane is shaking violently, you have a fire warning because the fuel tube cracked, the fire button might not want to stay pushed in, and now you can't see the instruments because the cockpit is filling with smoke.
It is a total workload saturation event, vibration, fire, smoke, and a likely return to the airport.
What's the move for the smoke?
The briefing notes that if the engine doesn't run down immediately, the bleed valve might not auto-close. The pilot might have to manually kill the bleed source, per the QRH, the Quick Reference Handbook, to clear the air.
It really emphasizes why pilot training is so rigorous. You have to be able to prioritize in that chaos. You can't freeze up.
Aviate, navigate, communicate, as always. But in this case, isolate the engine moves right to the top of the list.
There's one more layer to the human element here, and that's just knowing your aircraft. The source mentions logbook awareness.
This is for the pilots walking around the plane before the flight. You see them doing the walk around, checking the tires.
Sure.
But they also check the technical log inside. You need to know what configuration your engine is in.
What specifically are they looking for regarding this AD?
They are looking for entries regarding AD 2025-2604. If they see clamp removed, they know the aircraft is in phase 1.
Okay.
It's airworthy, it's safe, but it has that flexible tube setup.
And if they see TMS mounts replaced?
Then it's in the final configuration. Phase 2 is complete. It's good to go for the long haul.
It's interesting how these logbook entries tell the story of the plane's health. It's not just bureaucratic scribbles, it's the history of the safety fixes applied to that specific machine.
Absolutely. Every entry is a confirmation that someone has assessed the risk and applied the engineering fix. It's a chain of custody for safety.
So let's zoom out a bit. We've gone from the microscopic stress point on a fuel tube to the chaotic environment of a cockpit during an emergency. What is the big takeaway here?
Well, to summarize the journey, a bird strikes a blade. The blade breaks. The energy travels back and breaks a mount. The mount failure leaves a fuel tube unsupported.
The tube cracks.
The tube cracks, fire starts.
It's a terrifyingly logical sequence.
It is. And the solution is that mix of flexibility and strength. Remove the clamp now to let it bend, install stronger mounts later to let it hold.
And right now, as we speak, January 2026, this is happening all over the world.
The source mentions a high operational tempo. That's polite speak for everyone is rushing. Crews are scrambling to get these clamps off before that February 17th deadline.
Yeah.
If you're flying on an A320neo next week, there's a very good chance that plane has just been in the hangar for this exact procedure.
It's a good reminder that aviation safety isn't static. It's a constant process of learning.
We often say in the industry that safety regulations are written in blood, or in this case, fortunately, in scars. These ADs come from learning the hard way, interpreting the scars of previous flights where things went wrong, but everyone made it back to tell the tale.
It is comforting, in a way. It proves the system works, they found a flaw, they analyzed it, and they are fixing it across the entire fleet.
Exactly.
They didn't wait for a catastrophe.
That's the definition of proactive safety. They saw the pattern, those 3 confirmed instances, and they acted.
I want to circle back to that phase 1 fix, the flex fix, before we wrap up, because I think there is something really profound there that goes beyond just engines. Well, we usually think that to be safe, we need to be strong, we need to be rigid, unbreakable, we build walls.
Sure.
But in this case, rigidity was the enemy. The clamp holding the tube tight was the very thing causing it to snap.
That's a very valid observation. In structural engineering, we talk about compliance.
Compliance.
Yes, sometimes you have to design a system that can move with the forces applied to it, rather than trying to resist them. If you build a skyscraper that is perfectly rigid, it will snap in an earthquake.
Right.
You have to build it to sway. You have to let it dance with the energy.
It's a lesson that applies to just about everything.
I think so.
Yep.
Management, relationships, personal resilience.
Exactly. So here is my final thought for you listening today. We all have loop cushion clamps in our lives, things we hold on to tightly because we think that rigidity keeps us safe or stable. We think control equals safety. But when the turbulence hits, when the fan blade breaks, sometimes holding on tight is exactly what causes us to crack.
That's a powerful thought.
So take a look at the systems in your own life. Where are you holding on too tight? And where might the safest move be to just remove the clam, and let things flex.
Sometimes you have to bend to keep from breaking.
Thanks for diving deep with us today. We'll see you on the next one.
Eye safe.